Hello dear students, today we are going to see what colligative properties are and how osmotic pressure is a better colligative property than others. Solute particles, when they are added to a solvent, they interfere with the properties of solvent particles. For example, if you add non-volatile solute particles to volatile solvent particles, then means solution will have a lesser vapor pressure than the solvent. This makes one of the colligative properties, which is lowering of vapor pressure, okay, which we are going to discuss in due course of the topic. Now let's see what is the definition of colligative properties. The properties that depend upon concentration of the solution, that is the number of solute particles in a definite volume of the solution, okay. Next we come to types of colligative properties. One we just now discussed, lowering of vapor pressure. Second is elevation of boiling point. Third, depression of freezing point. And fourth is osmotic pressure. So first, lowering of vapor pressure. Let P0 be vapor pressure of pure solvent, PS be vapor pressure of solution. In that case, relative lowering means ratio of lowering, that is decrease in the vapor pressure divided by the vapor pressure of the solvent, okay. Now P0 minus PS by P0 equals to X, where is mole fraction of the solute particles. Now here X is equal to N by N plus N. N is number of moles of solute and capital N is number of moles of solvent. You know this about mole fraction. Mole fraction is number of moles of solute divided by number of moles of solution, okay. For a dilute solution in which number of moles of solvent is much more than number of moles of solute, this delta P by P0, relative lowering of vapor pressure, becomes small n divided by capital N. Small n, which is number of moles, can be given as amount of solute divided by molar mass of the solute, and capital N can be given as amount of solvent divided by molecular mass of the solvent, okay. We have replaced these values over here in this equation, and final equation comes out to be this: relative lowering of vapor pressure, W2 by M2 into M1 by W1, okay. And from here you can calculate M2, which is molecular mass of the solute. Now this molecular mass M2 is written as capital M in many books, so that is okay. Now next property is elevation of boiling point. If difference of see, we just saw that vapor pressure lowers as we add solute to solvent particles. This lowering of vapor pressure, what will it cause? It will cause elevation of boiling point. So second colligative property is actually related to first colligative property. And if difference in the boiling point of a solution, because it has increased, and a solvent is delta TB, that is delta TB equals to T solution minus T solvent, boiling point of solution minus boiling point of solvent, and this is directly proportional to the molality of the solution, okay. Now molality, you know, is number of moles of solute divided by mass of the solvent into 1000, right? Mass of the solvent when it is taken as gram. And when you remove this proportionality constant, Kb comes. Kb is molar elevation constant. So the formula for elevation of boiling point becomes Kb into M, where M can be given as W2 by M2, that is moles of the solute divided by mass of the solvent multiplied by 1000. And from this formula, delta TB formula, we can again calculate the molar mass, molecular mass of the solute, which is given by this formula, Kb into W2 multiplied by 1000 divided by delta T into W1, okay. Next property is depression in freezing point. This is again because vapor pressure lowers when you add a solute to a solvent. Freezing point also lowers, and this depression in freezing point can be given as, this formula is same as elevation of boiling point, as you can see, and only difference is that Kb is replaced by Kf. Yes, otherwise the formula is exactly the same, where Kf is molar freezing point depression constant. Okay, and the last one, osmotic pressure, which we are going to discuss in a little bit more detail. Osmosis, what is osmosis? When a pure solvent is kept in contact with the solution with semi-permeable membrane in between. So one side is pure solvent, another side is solution, and in between is semi-permeable membrane. Then solvent molecules start moving to solution side. Same process occurs when two different concentration solutions are kept in touch with semi-permeable membrane in between. Thus, movement of solvent molecules from low concentration, this is the definition of osmosis, movement of solvent molecules from low concentration side to high concentration side through a semi-permeable membrane is called osmosis. If the osmosis is taking place between pure solvent as the solution, and if you do not want osmosis to take place, you have to exert some pressure on the solution side. Now this pressure which you require to exert on solution side to stop osmosis is called osmotic pressure. Osmotic pressure of pure solvent is 0, and as you add solute, osmotic pressure of the solution increases. So osmotic pressure is a property which depends upon the concentration of the solution, that is number of solute particles in definite volume. Greater the number of solute particles, greater is the osmotic pressure, which is shown. Now these, what osmosis pressure is and what osmotic pressure is, can be shown by these two diagrams. Here you can see that this is a less concentrated solution where solute particles are lesser in number. This is higher concentrated solution, and now solvent particles are moving from less concentration solution side to more concentration solution side. And in this one you have this pure solvent outside, while inside it is solution, and this is at the bottom is semi-permeable membrane, and solvent particles start moving inside this container. And if you want to stop it, you have to apply pressure by a piston which is equal to osmotic pressure pi, and since pi is directly proportional to the concentration, it can be given as pi equals to CRT. Isn't it similar to gas equation? Now this is C is equal to molarity. Earlier three formulas we saw that one was mole fraction and two were molality. First one was mole fraction and then two were molality. Now this is molarity, number of moles of solute particles per liter volume of the solution, right, multiplied by R is gas constant, T is absolute temperature value, and this will lead to this formula because we are replacing N by W2, mass of the solute, divided by molar mass of the solute. And from here we can again calculate molar mass of the solute, which is W2 RT divided by pi V. Okay, let's come to the next and last topic, that is how osmotic pressure has advantage over other colligative properties. For that, first point is osmotic pressure values are much larger than other colligative properties. Therefore, you do not need much sensitive instruments. Okay, and it's easier to measure. Second point is osmotic pressure can be measured at room temperature, while other colligative properties require either boiling or freezing of the solution. So, for example, if you want to measure elevation of boiling point, you have to boil the solution. If you want to measure depression of freezing point, you have to freeze the solution. While osmotic pressure, you do not have to raise the temperature or lower the temperature. It can be measured at room temperature. And the last advantage of osmotic pressure is that in case of macromolecules, macromolecules means proteins and other biomolecules which get denatured at high temperatures, which get destroyed at high temperatures, can be measured with help of osmotic pressure rather than other colligative properties. And this question comes frequently, that in case of macromolecules, which colligative property you are going to use? Answer is osmotic pressure. I hope today's topic was useful for you, and I will come with next topic very soon. Till then, take care. Bye bye.